Now let's look at a particular implementation of list. Let's look at the ArrayList implementation. And when I say the ArrayList implementation, I don't really mean that. I mean a simplified version of the ArrayList implementation that's easier to understand but does most things the way that Java's ArrayList does them. One of the things that will be different about this implementation is that we're not going to allow null values in our list. This is different from Java's ArrayList, which can have null values in it. One important thing that is similar to Java's ArrayList is that the list will be implemented with an internal array. Since lists can grow in size but arrays can't, we're eventually going to run out of room in our array as we add things to it. Therefore, whenever our internal array is full and someone who is using the list wants to add another element, we're going to create a brand new array that is double the size of the old array. Then we're going to move everything from the old array into the new array, and we'll start using the new array to represent our lists. We'll throw the old array out. All of this happens behind the scenes, and the user does not see any of it. But I want you to know how it occurs. So let's look at some code. Okay, here's the first part of the ArrayList class. Notice that our class declaration indicates that we're implementing the list interface. The E inside the angle brackets is a type parameter. It represents the type of the elements in the list. For example, if a user declared a list of strings, the E would represent the string type. If a user declared a list of airplanes, the E would represent the airplane type. It's like a parameter to a method, but instead of representing a value, it represents a type. Lines 8 through 10 are the fields of our class. Sometimes these are collectively called the representation, because this is what we're using behind the scenes to represent the list. I say behind the scenes because all of this is hidden from the user. And we intended to hide it. That's why we're making our fields private. We have three fields. The first is our elements array. This array is going to hold the elements of our list. Now remember, arrays are a fixed size, so eventually we're going to run out of room with this array. We'll see what to do when that happens, but I want you to keep that in the back of your mind. Next, we have a size variable. The size variable is always going to tell us how many elements are in the list. Not in the array, in the list. The capacity variable, on the other hand, will always tell us the length of the array. Let's see how a new array is created, and this will become more clear. The constructor is going to create a new empty list. Since the list is empty, the initial size is going to be 0. However, we anticipate that the list will grow, so we're going to make room for new elements by setting the capacity to 10. Remember, the capacity will be the length of the array. Now in line 15, we're creating an array with elements of type E with a size of 10. You might think that we should just say new E bracket capacity close bracket here. And I would think that too, and I would actually prefer it. Unfortunately, because of the way Java handles type parameters, we can't do that. Java won't let you declare an array with a type parameter. That's because E is not a real type, it's just kind of a placeholder for a type. In any case, the code here will have the desired effect. We will create an array of type E with a length of 10. And here are a few notes about the code that you can review. There's nothing here that we haven't already mentioned. These are the two add methods. The first add method adds the specified element to the end of the list, and the second add method adds the specified element to the list at the specified index. To save space, instead of exceptions, we're just putting assertions here. Notice what we're asserting. For both methods, we're saying that the specified element should not be null. The real Java ArrayList implementation does not do this, but it makes it simpler for us if we do have this restriction. And on a personal note, I just cannot stand dealing with null values. And I try to eliminate the possibility of null values occurring wherever I possibly can. Because these assertions appear right away at the beginning of our method, you can think of them as preconditions. They effectively say that a user should not even try to call this method unless these things are true. Obviously, to be effective preconditions, they must be emphasized in the documentation. When we turn them into exceptions, they will be. The second assertion in the two-argument add method says that the index must be written within certain bounds. That makes sense because we don't want to add an element at a negative index. But just as importantly, we don't want to add an element at an index that is greater than the size of the list. Even, and I repeat, even if the underlying array is big enough to hold that index. That's because preconditions should be given from the point of view of the user. The user, the person calling the method, has to know what's expected of them. For example, suppose our list has size 2 and the underlying array has a length of 10. If you try to place something at index 6 in the list, you should fail because the list only has 2 elements. It doesn't matter that the array length is 10. Here are the preconditions in the form of exceptions, which is considered a best practice in Java. If the element is null, a null pointer exception is thrown. If the index is not within the correct bounds, an index out of bounds exception is thrown. While it's possible to catch an exception in Java, precondition violations like these are typically not caught. They usually just abort the program and print out a stack trace. Here are some of the most common exceptions you'll see. An illegal state exception is called when the calling object, sometimes called the implicit parameter, is in a state that is not appropriate for the method call. For example, if you had a method call remove first for a list and you called it on an empty list, then it would make sense if you received an illegal state exception. The illegal argument exceptions occur when an argument passed is not appropriate. Both exceptions we saw in the last slide were due to illegal arguments, but since we had more detailed or more explicit exceptions we could throw, that's what we did. So much for assertions and exceptions. Let's take a look at this code. First, look at the one-argument add method. We have an if block that says to do something if size equals capacity. Before we see what it's doing, what does it mean for size to equal capacity? Well, size is the size of the list, and capacity is the length of the array. So this is saying you need to do something when the list and array are the same size. Most of the time, the list and the array will not be the same size. When we first create the list, it's empty, but the array has size 10. When you have an array in which only some of the elements are important, it is sometimes called a partially filled array. The elements array is an example of a partially filled array. Only the elements in the array that correspond to the elements in the list are important. It doesn't matter what's in the elements that don't correspond to elements in the list. Okay, back to size equals capacity. This is saying that the array is maxed out. There's no room in the array to put another list element. Therefore, we're going to have to create a brand new array that is double the size of the current array. And we're going to have to copy the elements from the old array into the first part of the new array. That's what arrays.copyOf elements, capacity does. After that, we're going to assign the new array to the elements field. Once we do that, the elements field points to the new array. Once we have an array that has more room, we can add the new element and increment the size of the list. That's the one argument add method. What about the two argument add method? Well, the first part is similar to the one argument add. But after we account for the potential doubling of the array, we have a for loop. The loop starts at index size, which is the last element in the list, and goes downward until it gets to the desired index. And this is going to be a little bit easier to see graphically. So I want to add the letter J at index 3 in the list. Index 3 in the list corresponds to index 3 in the underlying array also. Right now, the letter D is at index 3. Remember, list and array indices start at 0. So I have to shift D, E, F, and so on. I have to shift them over to the right so that I can put J into the cell at index 3. So this is what I want to do. But where do I start? What is the first element to move here? Is it J? Is it D? Or is it I? Also, what's the last element to move? J, D, or I? Please pause the video and see if you can answer these questions. More than that, see if you can understand why those answers are correct. Ready? What's the first element to move? J, D, or I? Okay, suppose it was J. J has to go into position 3, where D is now. What happens if we just copy it there? If we copy J into position 3, we overwrite D, and D is gone for good. So that's obviously not what we want. So the answer cannot be J. What about D? D has to go into position 4. If we copy D to position 4, it overwrites E, and E is gone for good. So the answer can't be D either. Therefore, it must be I. If I moves first, it goes to an unimportant cell. Remember that elements is a partially filled array. Some cells are important, others are not. So I can move. Once I moves, H can move. Once H moves, G can move, and so on, until eventually you put D into position 4, and finally you put J into position 3. Therefore, the first element to move is I, and the last element to move is J. Okay, that was fun. Now let's do another tracing table.